Next is is laser sintering, also as selective laser sintering or SLS. If you see the image and if you remember, it's very similar to STL that we saw before. For again, for the same reason that it has its roots in STL. Why SLS is very important is that it's one of the only processes that can be used for 3D printing in metal. Yes, in metal you can print everything. Aluminum STL, you can use aluminum, stainless steel, copper, brass, whatever you want, you can print with that. Now this process works a little differently from the process we discussed before, in terms that it uses a powder instead of a liquid. Now this powder, because it's different from liquid, the whole aspect of how it is handled is very different from liquid. This adds another basically side to this 3D printer. It includes of a powder supply and a leveling roller. What happens is that this at the beginning of the process, this powder supply would be at the bottom, which goes from down to top, and the piston, similar to STL, goes from top to bottom, right? If you can see in the image, and if you have any questions, please feel free to ask them. So what happens is that initially this will be filled with this area would be filled with the powder of a certain metal. Let's talk about metals here. A metal. At the beginning, this would move up a layer. The roller moves from here all the way to this end of the machine. What happens is that this powder is then transferred onto this platform. The laser would basically be directed towards a certain part of the layer that needs to be melted. So instead of curing like we did in STL, in SLS, it is actually melting this metal powder into a solid form. Now each layer is basically a powdered metal melted to produce a solid form, and thereby binding it into an object. So that's how it forms the object. In the end, this would basically move up, and this would be at the bottom when the object is formed. After that, the 3D printing process stops, and you can basically pull out the metal object that is produced from the tank, and the powder that remains can be reused again. So basically all the powder that was unused from this is put back into the powder supply, and it can be used again for 3D printing. Important aspect of this is one of the only processes that I know of that can be used for 3D printing at the moment, and is commonly actually being used for 3D printing of metals. Again, this is not an exhaustive presentation. So again, there are a lot of other processes that can be used. This is what I know of in industry, which is being used very commonly. Okay, one more point that I missed out on this is that objects that are produced in metal using this process are not even close to as strong as an actual cast iron or an object produced using casting or molding. So what happens is that the bonds that are produced by just melting it by a laser are not as strong as that of a proper metal object that's produced. So this needs to have another post processing method known as hardening. So what that does is it's actually heated to a very high temperature, but not high enough for it to melt completely. What this does is it melts the powder just enough to bond with each other much better than it originally was, basically, and makes the object much stronger, and then it can be actually used as a product rather than a prototype. Okay, that's laser sintering. So what I'm trying to do with this webinar is also to get you an idea of what processes to use, and just to get a sense of what terms that you should know when you're working with 3D printing. So this is laser sintering, also known as SLS. So whenever someone says SLS, it's probably talking about laser sintering. STL would be surface stereolithography. So that's how you know when you're in the industry and when people are talking about this stuff. So you get a good understanding of what they're talking about. Now again, coming back to Inkjet. Now Inkjet is very interesting because it has its origins in Inkjet printing, a printer that we use at home. So you'll be wondering, so how do you use Inkjet? How do you use a printer that we use at home for producing an object, a 3D object? Now, if there are two ways of doing that. One is material jetting, like we discussed before. You just jet the material out and keep producing layers and layers and layers and layers. So instead of using an extruder, the material, basically the end effector that's actually going to supply this material to be formed into layers is an inkjet head, and it's just also known as a print head, and it just keeps printing this layer using an inkjet. This is not exactly a technology that I've seen commonly being used, but again, it's still a part of 3D printing, of the 3D printing process, right? Binder jetting, on the other hand, is extremely common and is a very good technology for 3D printing. Like a lot of the high-end products that are actually being used in the market and would have a good surface finish, good product quality, good strength, are usually done during binder jetting. So what binder jetting does is basically, uh, like if you see this image and if you remember the slide from before, it's pretty similar looking. The difference comes here. Instead of the laser, a binder jet actually has an uh, inkjet head, print head, but instead of depositing ink, it deposits something known as a binder, which is more like an adhesive. So what it would do is every layer, instead of trying to melt it to bond these particles together, it would actually spray on a form of adhesive, also known as a binder, and thereby binding the object together into parts. So basically, this adhesive will bind all the particles of this powder together to form the object. Again, very similar to STL and other technologies you've seen before. There is a powder supply tank that holds the powder, and there's a leveling roller which will push the powder onto each level as this piston moves lower while producing each layer of the object. And in the end, basically, it's similar to SLS. You would have this object in between all this powder, and you have to clean it up, and you remove the object and require some post processing to clean the powder out. Because it's an adhesive that's holding these particles together, the strength of the object is a function of, besides the powder itself is a function of how good the binder it is that you're using, that's going to hold this object together. Something to remember when thinking about inkjet printing. Besides that, inkjet has seen very significant success. If you know, HP and a lot of other companies that were originally producing printers, inkjet printers, laser printers, are looking into using the same technology to produce 3D objects and 3D printing. So you could potentially buy a HP 3D printer. I don't know if they're out yet, but you could potentially buy them soon enough. Okay, next. Now, this is the most commonly used method of 3D printing. It's called fused deposition modeling. Every 3D printer that people have at home or in colleges or wherever you've seen in manufacturing are probably 90% of the market is made of a fused deposition modeling printer. One reason being that FDM printers are super expensive. Sorry, super cheap. My bad. Sorry about that. Are super cheap. The material required in FDM is very cheap, and the materials and everything involved around it to have produce this product, handling of this material, keeping it clean and stuff of that sort, is very cheap, which makes it very easy for hobbyists and people who want to try this technology at home to use them. So an FDM 3D printer as an hobbyist, for a hobbyist, would be very cheap compared to any other form of 3D printing. So what this technology does, there is a build platform and there's an extruder. If you don't know what an extruder is basically a heated metal, and it has a hole in it. So the filament that passes through it, when it reaches the end of the extruder nozzle, it will be melted into liquid form. So that's so what a FDM printer does. It starts from the bottom, basically depositing a layer of melted thermoplastic at the bottom, and then building layers on top of it as at the same, like, while going along with time. So the build platform stays in place and the extruder moves. On the contrary, there are also printers in which the extruder stays in place and the build platform moves up or down. The filament is continuously supplied to it using these motors. So these stepper motors hold the filament and basically push it into the extruder as the extruder keeps moving and basically printing each layer. The videos that we saw in the beginning were also FDM, if you remember. They use an extruder to basically melt a filament and build the layers into eventually forming the object itself. I hope we have no. Again, I don't have any questions, but please feel free to ask me if there's anything. Okay. Yeah. So these are the commonly used processes and processes that we know very commonly. So FDM is one of them, and again, the most commonly used is FDM, and we'll go next to how we would select a process. So again, I have listed all the processes. This is not an exhaustive list, but if you wanted to pick a process to produce something, what process would you use? So there are certain criteria on basis of which you would actually select a process, right? So processes vary on build material. So processes that print metals cannot produce cannot produce plastic parts, and vice versa. So that's where you want to keep in mind what material you're using. So if you want to print in metal, you're limited by certain processes. If you want to print in plastics, you're limited by certain processes. So that's something that you want to keep in mind. Next is object strength. All processes vary. The object strength would vary from process to process depending on what object you want to produce. The surface finish that we discussed before, different processes vary in terms of the surface finish that you'll get for the final product. Processes vary in speed. Certain processes are faster than other processes. That's where you want to take that into account. Product geometries, that's again very important. What kind of geometries would best suit a certain process is very important. Cost varies from process to process, like I discussed before. FDM is very economic, but it cannot produce certain geometries, or it cannot print every material that you want, right? So that's why you want to take into account. You want to take into account all these aspects and the product that you want to produce, and then think about what process you want to go for. Now, like I said, FDM is the cheapest form, but you can buy a FDM 3D printer and print parts at home. But if you want to use other processes, you think your product is more suitable for some other processes, and if you obviously cannot afford to have these much more complicated printers at home, there are 3D printing services that are much cheaper, and you can just go online and upload your CAD file. Just build a good CAD file, convert it into STL, and upload it onto their software. They'll give you a good code for how much it's going to cost for you to just print this object, and you can order that object and they'll send it to your house. So don't ever feel limited by the fact that other machines are very expensive. There are services like that you can always use. Okay. Sorry, my mouse is a little more sensitive. So yeah. So coming back to what materials can 3D printing produce? So this is at the moment. At the moment in plastics, the most commonly used plastics are PLA and ABS. PLA is polylactic acid, and ABS are the most commonly used materials used in FDM. That's mostly because they work well in the environmental conditions that we have, but there is no limitation to what materials you can use with FDM. A lot of materials can be used other than these, but these just work well and are easy to handle. There are not a lot of challenges that come up when you're trying to print these. We discussed photopolymers. So photopolymers and liquid resins, we've discussed about that in a very specific process. Then metals, again, aluminum, steel, stainless steel, any metal that you can think of can potentially be 3D printed. Again, it's limited by the processes and the technology right now. We discussed food. Another important one is ceramics. Ceramics, a lot of hobbyists and artists have been able to produce a lot of things with 3D printed ceramics. Then, like I said, any material and basically all materials can be 3D printed. It's just that at the moment, we are limited by technology, but students and engineers and other people like you who are watching this webinar, you're always open to basically look into different materials. There are a lot of universities and companies that are looking into specific materials and their 3D printing application. For example, the university I studied at, where I learned about 3D printing, one of the professors was working with 3D printing of graphene. Graphene is an ultralight material. It's very difficult to 3D print, but they have had such good success. They have actually had their name in the Guinness World Records for being able to 3D print the lightest material on the planet, or graphene, basically. It's ultralight. If you can read about it, if you get a chance, it's at the University of Buffalo in 3D printing, 3D printed graphene. Okay, moving forward. So I'm going to give you like I know this point probably I'm running out of time, but let's just going to wrap it up soon enough. So we'll just quickly talk about the steps that are involved in 3D printing. So I'm going to talk about the 3D printer I have, which I discussed was FDM, Fused to Precision Modeling 3D printer. This is the printer I have. I have a Creality CR10 V2. Again, I'm not associated with this company anyway. It's just the name I wanted to put out to give you an idea of how you would see something like that. So I have a Creality CR10 V2. This is the printer. This is what it looks like. This outer covering that exists over here is something I have put. This gives it protection from environmental. So when using FDM, temperature control is very important because external temperature can definitely affect your print quality and systems. Print quality and other issues can be caused, which we'll actually discuss in some time. So this is the external 3D printer. It comes with a controller, and this is where I put in the filament. The filament goes inside through here. And like we discussed here, this is the extruder that would actually print the material. So if you see this, this is not my printer. This, I think, yeah, anyways. So this is another printer, and that's basically how the filament works, and eventually you'll see the product. So again, this is FDM, Fused to Precision Modeling, something that you need to know when you're buying a printer. Max printing size is 300 by 300 by 400. As you can see, the Z-axis is up to 400. It's a much longer. Very useful for me because a lot of times I print brackets and support structures for the part places I work in. Objects, actually physical objects that I need to use for mounts and all sorts of stuff. A lot of times I need jigs, test jigs, and part holders, and for parts that are as big as 350 mm in size. So the nozzle diameter, most of the times when you buy an FDM printer, will be 0.4 mm. Don't be surprised by that. It's just that it's just standardized. You can go lower, I guess, if you wanted to, but you would have to have a good understanding of what changes you need to make in the design if you're going for a lower nozzle size. Precision being plus minus 0.1 mm means that if you have designed an object, the offset, the worst case scenario would be, it would be 0.1 mm bigger or smaller, go on both sides of that. Layer thickness is 0.1 to 0.4 mm. By that, I mean that you can set it to be either 0.1 mm thick to 0.4 mm thick, which you can do during the slicing process. Again, this is just so that you have a good idea. This is not the complete exhaustive list, but this is just to give you an idea of what aspects you need to keep in mind when you're looking into this technology. Okay, so quickly going through the process in one slide, if I wanted to explain how you would go from a digital design into a 3D printed object. So originally you would design an object in CAD. There are a lot of CAD softwares. I usually use Inventor, but again, it's not limited. Please feel free. You can use any and every CAD software basically can be used to produce a 3D printed object. So you would start with a CAD model. When saving the file for this particular geometry that you've produced, you would save it as an STL file. What this does is converts it into the STL format, which we discussed before, stands for stereolithography. And that's a very specific format that is very helpful when using it with the slicing software. So there is something known as a slicing software. What this does is it will pick up the geometry of the object that we produced in the CAD model. It will slice it. What we discussed, as we discussed, slice is basically every individual layer that the 3D printer is going to print. Now, a 3D printer cannot read STL files, CAD files, or anything. What it needs is the G code. So what a G code does is that G code tells the printer how it's supposed to move in such a way that it can produce a 3D printed object. And while doing that, how much material should it be basically extruding at that point? How much, when should the fan or heater be on during this point? What should be the bed temperature during this time? So what the slicing software would do is pick up this STL file, convert it into a G code, which is also basically, to explain what a G code is, it's a file that the 3D printer can understand and thereby produce the physical object from the digital design that we received from this part. So in the 3D printer, you would load the G code, which we received from the slicing software. The most commonly used slicing software is Cura, but again, it's not. I'm not associated with any of these companies, so please feel free to use any and experiment with every slicing software. Some softwares have their own issues, some have their own advantages. There are things that you can change and not change in certain softwares, and I've just found Cura to be very helpful with that. You will also be loading the build material, which in this case would be a filament, and that's it. You press the print button. A few hours later, you have this object. Now, to give you an idea of why I find this so intriguing, is that this is a bracket this is a sensor mount. I mount a sensor onto this. This was a very specific custom sensor that you don't get brackets for, right? So it would have been so painful for me to actually build this out of metal or use some conventional process to produce this kind of a bracket. I basically built this bracket in an hour. So basically, I can use this for anything and everything, and it's been very useful for me, especially in the field I'm working with. But again, it's the opportunities in this field are limitless. Okay. I hope you have a good an understanding how simple this is. But again, if you have any questions, please feel free to ask. Okay, some important parameters while slicing. So we discussed about the slicing software. I'm going to quickly go through them because I think I'm kind of running out of time. So quality is something that you define in a slicing software, which would define how well the print looks and how good the resolution of the print is. Next is the shell. Like I said, most 3D printed objects are assumed to be hollow because this is just an assumption. But you can, if they're hollow, you need to define the thickness of the outer wall. Now that's very important. It would define the strength of this object, right? Now, like I said, it starts as hollow, but you can define the amount of infill the material is printed. You can go from a completely hollow object that would be 0% infill to 100% infill. That would be an object that's not hollow at all. It's like filled with materials. It's super heavy. On the other hand, you can also select certain mid ranges like 60%, 70% infill. What that does is it will still have something in between, but it wouldn't be completely solid. You need to adjust material settings if you're changing the build material on the same printer. That would adjust a lot of the temperature settings when you're printing. There's support. Some geometries may need support structures. So a lot of the geometries have something known as an overhang, and that needs support structure. Now these things that I'm talking are again very specific to FDM. They do not apply to a lot of the other processes. Build plate adhesion is another something. So a lot of times there's a problem known as warping, which we are going to quickly discuss in the next stage. You would need something known as a build plate as adhesion, which you need to define when using the slicing software. Okay, so now that we've spoken about FDM, and a lot of you might think of buying an FDM printer and start printing, you might be these issues that we could talk about happen very commonly. So I would just want to let you know that don't be deterred by them. They're very easily solvable, but these happen all the time. So some of the issues that when you're working with FDM, you'd realize are you'd know about is warping, cracking, layer shifting, Z wobble, stringing, curling, and something known as elephant's foot. So whenever you're working in manufacturing or industries that use this technology, these are something words that might come up from time to time. These are basically issues that happen with FDM, which are easily solvable. But if you're a beginner and novice to this technology, don't feel deterred by it. It's very easy to solve these issues. So warping. Now, if you remember what we've discussed, and if you know how if you understood what we're talking about, you would see that 3D printed again uses a layering approach. Now you're basically 3D printing with a thermoplastic. It's a solid. As we all know, solids expand on heating and contract on cooling. Now when you're using a layered approach, the lower layer, the initial layers will actually be heated first, printed, then the upper layers, right? So by the time the upper layers are being printed, the lower layers cool down. What happens because of that is the lower layers start to contract while the upper layers are still in their expanding stage. I hope that's I put it in words easy enough for everyone to understand. But again, please feel free to question me. What this causes it to do is the contracted layers lose contact with the build plate because of their contraction while the upper layers are still expanding. Now in FDM, it is very important that because the lowest level, which is coming in contact with the build plate, is going to hold all the above layers. It's very important that this process of warping does not happen. Okay, I think I didn't bring that up, but basically this problem is called warping and happens very commonly with FDM. It usually happens when your so most 99% of the time build plates are heated. That's so that the lower layers are kept heated even though the upper layer is being printed. And that's very helpful in 3D printing with FDM. So, but this issue is very common and happens all the time. A lot of times. So, for example, my build plate, the printer I have, even with a heated build plate, this issue happens very commonly. Now, that is because I stay at a place that's very cold. Now, the environmental temperature is actually affecting my print quality, and this happens all the time. So that's why, as we saw before, I have the temperature controlled heated, basically an enclosure that you can again buy around the printer that you have. A lot of printers that you can buy in FDM come with an enclosure with a temperature control system, which can keep the temperature inside the enclosure very close to the room temperature, and thereby give you good print quality and avoid problems like this which are working. Yeah. Next is cracking. Cracking is another issue. It does not happen as much, but I have seen it happen from time to time. What happens is that uh, when when a layer is being printed on top of the top of another layer, the layer above basically solidifies even before it can basically bond with the lower layer. So what happens because of that, the bond between two layers is very weak, and even though the object is printed and looks printed, it will basically just fall apart when you put any stress on it. And it's again a problem that rarely happens, but if it happens, it can be controlled by using a temperature controlled enclosure, and also by making sure that your temperatures are set correctly so that the object is not solidifying before being basically printed on top of another layer. And this will something that you'll do during the slicing process. This issue, again, this happens pretty commonly, but it's not that bad. I think in terms of object impact, it only affects us aesthetically, but as a product, it is not affected so much. It's called stringing. Stringing happens when the temperature of your extruder is much higher than it needs to be. Actually, it's not even much higher. It's even if it's slightly higher than it needs to be, or if it's the environment is very hot on a particular day, what happens is that opposite to what we saw in the last slide, cracking, instead of the layer adhering to the lower layers, instead of basically solidifying in what we saw in the last problem, in this problem, it does not solidify within time for the extruder to go to the next layer. What happens is that it prints one layer correctly, but because the material is still hot and not solidified, it sticks to the extruder, and the extruder, while moving to the next layer or moving to the next part of the geometry of the same layer, it will just drag the thermoplastic. Again, they're plastics, right? So plastics stretch a lot. So instead of being stuck to the geometry of the object that you're producing, it gets stuck to the extruder and produces these strings. Again, it's not a big problem. It can be solved by having good temperature control. And even if it does happen, it can be just cleaned off by post-processing by some an abrasive of some sort, like sandpaper. But again, there are multiple ways. It is much easier to just get good temperature control and produce the object correctly in the first time, right?